Yeah, thank you for the intro. Yeah, since it's the last session of today, I guess people are feeling tired. Probably want to go home or go travel, come here for vacation or whatever. So yeah, I want to do a short survey about the background of the audience. So how many of you are doing data engineering over here? Okay, pretty much everyone. How many of you are doing the data infrastructure, building the okay? Some of you, okay, that's good. Yeah, I think it's a perfect talk for you guys. And I feel like all of us deserve a good race because we are actually kind of like the god of medias, turning the useless data into gold, right? So we have a golden touch. And I think, today I'm gonna talk about aggregation pushdown and tell a little bit about why it's important and why it's useful in many of the data pipeline, actually. So who are we? Huaxin is my colleague, and she is Apache Spark PMC, working at Apple. And I'm also a Spark PMC. I'm supporting the Spark team right now, working at Apple as well. So at Apple, we use Spark a lot for various of different data pipeline, actually. And if we are able to save, let's say 10% of the compute resource, it can translate to millions of dollars per month. So that's why we invest a lot of time and our engineering effort to make Spark run faster, in our data platform. And we also make it open source because we truly believe that open sourcing them will be able to help the entire community. So we work on several features, and we have like 5 talks from Apple this time at in this AI Data Summit. We're gonna talk about all the innovation we work on Spark, and also some of them are on Iceberg actually. Okay, so let's talk about the query of the interest. So let's say we have a query. We want to look at the min-max, or how many records of the data from a table. And now how Spark work? How Spark work is that Spark is currently doing a full scan. We need to scan through the entire data set, bring all the records of the data into Spark, and Spark do a aggregation, hash aggregation to figure out what's the min, max, and all kind of statistics. And it's really expensive, actually, because it involves a lot of data movement from data source to Spark executor, and then Spark do the computation. So the goal of the pushdown, aggregation pushdown, is that we don't want to do a full scan. We want to leverage on the data source to get the statistics. And there are 2 types of scenarios we are facing. One is for JDBC data source. If we are able to push down this kind of statistics to JDBC, then we will be able to use JDBC to do the actual computation, and we just get the result from JDBC. And for file-based tables such as Parquet, ORC, or Iceberg, a lot of statistics is already in the metadata, in the footer, right? So we don't need to do full scan. For example, if you want to get a mean of a table or certain column of a table, you can look at the footer of each Parquet file, and then you get a mean of each Parquet file, and then you get all of them, and then you just do a global mean of all the footer data information, right? So then you don't need to go through record by record, pulling all of them into Spark and to do the computation. So this is the basic concept of the idea. Okay, so before we go into more technical detail, I want to share a little bit about data source API and what is it inside Spark, because this can build some knowledge about the background of the concept. So data source API is a way inside Spark that we are able to integrate and interfacing with external data source, such as Hive, Parquet, ORC, JDBC, and Iceberg. Because Spark is a compute platform, we don't have the storage side. So storage we rely on external data storage. And data source API is a set of framework that we are able to interact on both areas. And data source API also is a pluggable mechanism that each vendor or each data source, a team can implement their own implementation of it, and also, it provides certain method that be able to interact with Spark SQL query optimizer, in terms of like a catalyst engine. And also it has an interface for a push-down operator for data source, so we can do further optimization. And also, as you know, filter push-down, column pruning is also being implemented in this layer. So we have a data source v1, and the reason why we talk about it is that we have data source v2. And there's a limitation in data source v1. It has a really strong dependency on Spark SQL in terms of SQL context, and also, it's also dependent on data frame. So for people who want to implement a new data source implementation, it's going to bring in really heavy dependency, which is something we don't want to see. And also, it doesn't support columnar and some of the streaming feature, and this also doesn't support like some of the transactional support, such as some of the feature that has been implemented in Iceberg. So data source v2 is trying to address those issues as well. And another issue is that for the new operator pushdown, the support is limited in data source v1. So let me hand over to Hua-Xin, and she's going to talk about more on data source v2 and how it works.
Thank you, DB. Since there are some limitation in data source v1 API, Spark introduced this data source v2 in 2.3. The data source v2 API has a set of Java interfaces. These Java interfaces are located in Spark SQL connector package. In the connector package, it has several sub-packages. For example, it has a read package, a write package, and a catalog package, and several other packages. In the read package, it has all the read-related interfaces. It has a batch interface for batch reading. It has a scan interface for scanning data. It has a scan builder interface for building scan. And it has several of the operator pushdown interfaces. Remember, one of the data source v1 API, its limitation is it is hard to push down a new operator. In data source v2, we don't have this limitation anymore. If we want to push down a new operator, we can simply add a new operator pushdown interface. In this read package, we have added several new operator pushdown interfaces recently. Originally, we only have this filter pushdown and required column pushdown interface. Recently, we have added supports pushdown aggregates interface. This is the main thing we're going to talk about for today. We have also added a pushdown limit and pushdown table sample interfaces. In order to have a better understanding of how the operator pushdown works, I will briefly talk about where the query plan gets generated and where the query optimization rule gets applied, so we can get a better picture of this aggregate pushdown. So for your production system, you have a Spark driver, and you have a bunch of Spark executors. In the Spark driver, the driver will determine the schemas, and it will also generate the query plans. It will also create a partition reader factory and send it over to the executors. On the Spark executor side, it will create a partition reader. The partition reader will fetch data from the external storage, and then it will process data. This slide shows the query plans. This is a very famous picture. I bet everybody has seen this picture before. So basically, the driver will create an unresolved logical plan first from the query or from the data frame. And then the Spark driver will check the catalog to apply the analyzing rules to generate the resolved logical plan. And then it will go through the logical optimization phase. Basically, it will apply a bunch of optimization rules to generate the optimized logical plan. And then it will go through physical planning to get the physical plans. For our operator pushdown, it will happen at the logical optimization phase. So basically, the data source v2 has several of the operator pushdown rules to push down the operator to the external storage. Originally, Spark only has a pushdown filter and pushdown required column. We have added several new operator pushdown recently. In Spark 3.2, we have pushdown aggregate to JDBC. In Spark 3.3, we have pushdown min, max, and count to Parquet and ORC. We have also pushed down the data source v2 filter we also include push down the functions in the v2 filter. And also, we have push down limit and also push down table sample. This slide shows the data source v2, the operator push down rules. As you can see in the slide, in the push down rules, we will first push down sample, and then we will apply this filter pushdown rule, and then we apply the aggregate pushdown rule. And after that, we will push down limit, and also we will push down the required column. I will talk about the JDBC aggregate pushdown first, and then my colleague DB will cover the Parquet aggregate pushdown, and he will also talk about the Iceberg aggregate pushdown. So in Spark, in data source v2, we have this built-in JDBC implementation. There is a JDBC scan builder class. Initially, this class only implements filter pushdown and required column pushdown. Recently, we have made it also to implement the suppose pushdown aggregate to push down the aggregate functions. So in data source v2, we have added this new option called pushdown aggregate. The default of this option is false. If set to true, Spark will push down the commonly used aggregate function to JDBC data source. For example, it will push down max, min, count, sum, and average to the JDBC data source. The filter will be pushed down along with the aggregate, and the group by will also be pushed down. If there is only one partition, the aggregate pushdown is a complete pushdown, and Spark doesn't need to do a final aggregation. But in most of the user cases, we will have multiple partitions. In this case, the aggregate pushdown is only a partial pushdown. Spark will need to do a final aggregation in the end. Let's take a look at an example. This example shows one partition complete aggregate pushdown. In the query, we have a simple select star from table, and then we have a filter, and we have a group by column, and we also have a simple aggregate function min. If we want to see the query plan, we can do a explain. So this slide shows the query plans. On the top of the slide, it shows the analyzed logical plan. In the analyzed logical plan, you can see we have aggregate on the top, and then underneath it, it has a filter. Underneath the filter, it has a v2 relation. It has all the columns there. In the middle of the slide, it shows the optimized logical plan. At this time, we have already applied all the operator pushdown rules. So in the optimized logical plan, we don't see the aggregate anymore because it has been completely pushed down. We don't see the filter anymore since it's also being pushed down. We don't see the unnecessary column anymore since this has been pruned out. We can also see in the optimized logical plan the aggregate function min has been applied to the column salary. On the bottom of the slide, in the physical plan, we can see the pushed aggregate. We can see the pushed filter. We can also see the pushed group by expression. This slide shows the partial aggregate pushdown. In this example, we have multiple partitions. The aggregate pushdown is partially pushed down, and Spark will need to do a final aggregation in the end. So in the example, we specify the number of partitions. We specify the lower bound and the upper bound of the partition. And we also specify the partition column. In the query, we have a filter, and we have a simple aggregate function sum. So this slide shows the query plan again. So again, on the top, in the analyzed logical plan, we will see aggregate function for sum. We can see the filter, and we can see the V2 relation. In the middle of the slide, that's for the optimized logical plan. Since we have already applied for all the operator pushdown rules, the filter has been pushed down, so we don't see the filter anymore. We don't see the unnecessary columns anymore since this has been pruned out. And we can see the aggregate function sum has been applied to the column salary. Since we have more than one partition, for example, this is a partial aggregate pushdown. Spark will need to do a final aggregation on the top. That's why we still see the aggregate function on the top of the V2 relation. In the physical plan, we can see the pushed aggregates and the pushed filters. Let's take a look at a benchmark. This benchmark is done using a TPCH query 6. So I have the benchmark result for both the query time comparison and also for the transferred data comparison. So for the left-hand side, it's for the query time comparison. So the blue column shows the query time with aggregate pushdown. The green column shows the query time without aggregate pushdown. As you can see from the result, if we don't do an aggregation pushdown, it will take about 4 times as much time as the blue one, which has the aggregate pushdown. For the right-hand side, it's the comparison for the transferred bytes. If we don't push down the aggregation, we will need to transfer about 4 gigabytes data. So the green column shows the data we need to transfer without aggregate pushdown. With pushdown, we only need to transfer 17 bytes of data. I did plug the 17 bytes, but since it's so small, it doesn't even show there. So this is all I have for JDBC aggregate pushdown. I'll hand the control over to my colleague, who will continue with Parquet aggregate pushdown.
Thank you, Hua-Xin, for the JDBC aggregate pushdown. So I'm going to continue to talk about Parquet aggregation pushdown. And I guess many of you are using Parquet as the data storage file in production. So I think it's going to be of interest to you and me to share about some of the basic idea on how Parquet works. So inside one Parquet file, typically we have multiple row group. And for each row group is a minimal self-contained element that containing all the row of the data that stored inside one row group. And as you know, Parquet is a columnar data format. So how it's stored is that inside a row group, you have multiple column chunk, and each column chunk represents one column of the data. So inside Parquet, you will be able to read certain column without reading the entire data, because each column is stored in one column chunk, right? And inside one column chunk, we also has its own metadata in terms of like min, max, and count, all kind of statistics that can be used for predicate pushdown, for example, or they can be used for aggregation pushdown that we're gonna discuss later. Yeah, so I think this show more detail about the structure of the Parquet. So like inside one column chunk, what kind of metadata you have. Okay, so two things I want to notice is that data source v2 is not enabled by default right now. So if you want to try out this feature, you have to enable data source v2. And also the Parquet aggregation pushdown is not enabled by default as well. It's a new feature we just merged into the open source community. So if you want to try out, you need to manually enable that. And now we are able to push down min, max, and count statistics to Parquet in this implementation. And we use the statistic information inside Parquet row group metadata to derive the global min, max, and count. And we do the final aggregation as Spark. So let's talk about one example. So let's say you have a table, an event table, and you have a partition column called year, and then you have a bunch of Parquet files over there, right? And let's say you want to push down, you want to find the mean of a certain column. How do you do it, right? So let's say if the filter is on the partition column, okay? So that implies what? That implies the filter won't actually apply into the Parquet file itself. So the filter won't change the statistics of the Parquet file because it's applied on the even more top level, on the partition level, right? So the statistics inside Parquet file won't be changed. So how Spark do the min, max, or count? Then in this case, we would be able to just read all the footer information, getting the min and max or count for each Parquet file. And then we can, from there, we can do, global, we can derive the global min or global max or global count. So this is how you work. So all the data we read is only the footer of each Parquet files in this scenario. However, if your footer is not on the partition column, what does it mean? That means the filter will change the statistics of the file because some of the record inside Parquet can be filtered out. So the statistics inside the footer won't be accurate. So that's the case where partial aggregation or aggregation pushdown cannot be applied in this scenario. And similarly, a group by has to apply only on the partition column as well. Is a limitation in terms of how the metadata is being laid out. Okay, so let's talk about one of the example. So to set it up, you can set it up, enable this feature pretty easily if you want to try it out. And then you can do, let's say you select max ID, min ID, and count from a table. And we can look at the execution plan. Right, so before the aggregation push down this feature, what happened inside Spark? What's going on is that Spark gonna read the entire ID data from the Parquet file, load it into the executor, and then we do a global scan. And then from there, we derive the statistics. And the statistics is really important because many of the business use case is just asking for the statistics from a source of truth table. And I know many companies run into this limitation. So how they do it is that they create a secondary table that only contains the statistics of the source of truth, which is kind of annoying because you need to keep making sure like the two tables are in sync, and making sure like they are consistent, right? So with this feature being enabled, you can see the push aggregation. So the max, min, and count will be pushed into Parquet file. So from Parquet file, we get only those metadata back to Spark. And from Spark, we just find the global max, min, or count from those metadata. Okay, so let's talk about the benchmark result. So overall, we see like a 20-time performance scan comparing with or without aggregation pushdown in some of the synthetic use case. And in most of our production workflow is also improved a lot, lots of gain. It's kind of like for data science or data engineer, when they type enter, they can go out and grab a coffee and come back to see the result. But right now, it's kind of immediately returned back. So they don't have time to take a rest. I know they don't like me to do this kind of optimization. But they give them the result faster. And since Iceberg is a table format, we decided to use at Apple. So we are also working on improving the aggregation pushdown within Iceberg. It's a feature that we are internally developing right now. And once it's ready, we will also make it into open source as well. So yeah, thank you. So yeah, thank you. Yeah, so just a couple notes. So I think we are doing a lot of cool stuff at Apple, a lot of like upstream code engineering, and also like even on the data engineering side, we have a lot of good projects, and we are hiring. So if someone has interest to look around, just feel free to reach out to me. Yeah, thanks. Question time.
Yeah, one thing that you noted is when you are doing an aggregate pushdown, that there has to be a partition filter just to make sure that the query is accurate and there's right aggregations. Let's say that you had a unpartitioned table, and I still did an aggregate pushdown. I think that the page, I guess footers would still have accurate min and max.
Yeah.
So I'm just asking, is a partition filter required to do an aggregate pushdown if it is a flat table, or would you still be able to take advantage?
Yeah, it's a good question. Yeah, so I think it's the current implementation limitation. So we are thinking about, as you suggested, right, extend it so that we can do like in the page label. Page label has its own metadata, so we would be able to simply just put out couple page and then use the page information to get a global. So that would reduce a lot of read as well from the actual content of the Parquet file. But it's not being implemented, and something we are consider and thinking about to work on that in upstream. Yeah, but we not educate customer or user of the data platform to try to making sure that the data is laid out in this format. But I think this is a limitation right now that we can potentially eliminate. Yeah, good question.
Thank you.
When you said this Parquet file, when you do push down, you read the footer and the header. So if the Parquet file is compressed like the standard or whatever, do you need to decompress the file to read this?
Oh, good question. Yeah. So I guess you are talking about splittable, non-splittable compression codec, right? And typically people use ggzip or gstandard to compress Parquet. But being said that the compression is done in the page label inside a Parquet file. So basically, each time when you decompress it, you only have to decompress the page if you are reading the actual content. And then the footer is its own, compression actually. So basically, you can just pick up the footer and then just get a range of the data, because in Parquet file, in the bottom of Parquet file, you're gonna get offset of each kind of data. So you can just get a small range of the data out from the Parquet and decompress it, and then you can use it to get the metadata. So you don't have to decompress. In short, you don't have to decompress the entire file.
Cool. Thanks.
Yeah.
Is there any restriction on the data types? Like, for example, the max and min, are they kept for all kinds of data types, or they're for built-in types?
What's the question?
So are you talking about, is there any external data?
Is there any restriction on the data types? Like, for example,
we have some limitation for certain data types. For example, for this string data, because in Parquet, string has a limitation that it might truncate the max and min. So actually, the pushdown doesn't apply to string type.
I see.
Yeah, that's the current limitation.
Thank you. And for JDBC, do you support nested expressions, like, for example, max of expression under the max?
Oh, I didn't quite catch that. So for JDBC?
if we have nested expressions, like max of another expression underneath,
Oh,
do we push down that or no?
no, currently we don't push down
Thank
that.
you. Thanks a lot.
Yeah.
Thank you for the presentation. Just one query. Have you tried this on filters for multiple columns, or have you tried that?
Yeah, filter multiple column will work, as if they are on partition columns. Because as I mentioned, the current implementation is pretty basic, as long as the filter is on partition column, the filter doesn't change the statistics of the Parquet file, then it's gonna work. Right, but potentially we will be able to make it much more fine-grained on the page level, but it's something we don't implement yet.
Got it. And for best efforts, preferably some data analysis beforehand to find out like how many number of partitions would be ideal.
Sometimes require some of the understanding of data that we have to, massage it so that it's gonna work in this kind of scenario. Yeah.
Thank you.
Does a pushdown work for only simple type, or it also work for those complex types like array or map or nested array in map kind of stuff?
That's also the current limitation. We don't push down for the nested types.
Yeah, but in theory, it will work because the nested type inside Parquet is actually stored in a columnar fashion. So we have the statistics of that, but that is not being implemented yet.
Nested column, meaning, see if we have column 1 dot column B.
Yeah.
Then it's the pushdown will not work for column B.
Yeah, currently it's not working, but the metadata is there in Parquet. It's just not being implemented yet.
Got it. Yeah. How about, see there's a top level column, and this column is array type.
Is what type?
Array.
Array, okay.
Array. Let's see, array of strings. Will the pushdown work for the, see if we're trying to find out the max number on this column across all the values in the array.
Okay.
If it's, we push down the count, but we don't push down the min and max yet for the nested column, even for the top level.
The array, top level of the array type.
Got it. How about map?
I think in theory, map should be able to implement it. I don't know whether it's been implemented yet, because map inside Parquet is also stored as a separate column, and then we reconstruct it into a map. When Spark construct the data frame or whatever format. But in theory, we should be able to do it. But I don't know whether the implementation has it or not.
Right now, we only push down count for the map for all the nested types.
Got it. Thank you.
I think June is asking because in Adobe, we have heavily nested rows. We have all our data are heavily nested. That's why I believe he's asking about individual types.
Mm-hmm. Looking forward to your contribution.
Right, any more questions?
My understanding is that data source v2 also implements merge during write. I guess my question is, do you guys see yourself making further improvements? Like I know some JDBC, like some RDBMSs will support merges. Like MySQL has some limited support for merge. I imagine at Apple, you're probably doing more reads from those.
Yeah, merge only.
Yeah, so do you guys see enhancements coming to write operations as part of merge, as part of data source v2? And then I guess I would say maybe another question is, just as you look at data source v2, are there any really good implementations or perhaps ones that you think might be lagging a little bit behind?
You want to go?
I'm not so sure.
Okay, we can discuss offline. Yeah,
of course.
because I think it's a really long conversation.
Oh, so all good.
Lots of good questions. So, yeah.